Right. Okay, well then first I would like to thank Job and Bernard for organizing this and inviting me to speak here. And of course, I welcome everybody to this talk. Thanks for joining. So yesterday in this conference, we had the real groups, and today it will be about the p-adic groups. So, well, apart from that, the title doesn't give away much. So let's go to the next slide. What do I mean by a p-adic group? So for me, this means a group over a local field, and this field is non-Archimedean. So it's not Archimedean like the real numbers, it's non-Archimedean. And I include here also the local fields of positive characteristics. And then I'm interested in the smooth representations of such groups. And well, since these are p-adic groups, let me specify that these are smooth representations on complex vector spaces. Of course, that's obvious if you're used to real groups, but for p-adic groups, there are many people looking at representations on other vector spaces, say of positive characteristic. So, well, I shall want to look at Bernstein components in this talk. And well, let me briefly recall for starters what this was. So there is, well, say the category of smooth complex representations of this group G, which I denote by rep G. And well, Bernstein showed around 1982 that this category admits a decomposition into a product of subcategories called Bernstein blocks. And well, these subcategories are indexed by some data consisting of Levy subgroups and certain supercuspidal representations. And well, the goal of this talk is to understand what does one of these Bernstein blocks look like. So I assume that a supercuspidal representation and a Levy subgroup are given. Doesn't matter to me how you get them, where you get them from compact induction or whatever way, just one supercuspidal representation of one Levy subgroup. And then I want to analyze this block rep GS. And well, of course, it has been done many times already, and in many cases, this has been worked out completely. So it's already known what one can expect, more or less. And I shall try to work in that direction. So things you can expect is that this block is described by an algebra which admits a quite nice presentation. Typically, it will be some kind of Hecke algebra. And well, okay, I shall try to work there. And if you have that, you can ask further questions like the fundamental question of representation theory. Can you find all irreducible representations and can you classify them? And if you know that, or have a satisfactory answer to that, you can ask further questions like, can you describe various classes of representations? Here I have mentioned tempered representations or unitary representations or square integrable representations. And well, the very quick summary of my talk will be that the answer to all these questions is yes, but well, with small caveats, which we will see later on. Okay, so now let me discuss things in more detail. So yeah, the results I will present here are well, precise, but it's very difficult to state them precisely. So I will first give various rough versions, and only at the end we will have some more precise versions. So let me say something about these Bernstein components in more detail. So it all comes from the notion of parabolic induction of representations. Well, probably well known to everybody who attends this conference, that you start with a parabolic subgroup and then you have a Levy factor, say M of it, and you can well, inflate representations of M to representations of P and then induce to G, and that's parabolic induction, and that's a useful operation. And well, in the world of p-adic groups, this gives rise to the notion of a supercuspidal representation. And a representation, or at least an irreducible representation, is called supercuspidal if you cannot obtain it by inducing something from a proper parabolic subgroup. And well, there are various ways or equivalent ways to describe supercuspidal complex representations. And one other way to say it is that the matrix coefficients of such representations are compactly supported modulo the center of the group. So supercuspidal in particular means something like it's a square integrable representation, but in a strong sense that the matrix coefficients are more or less compactly supported. And well, associated to the notion of supercuspidal representation is the notion of supercuspidal support. Namely, well, suppose you have an irreducible representation which is not supercuspidal, then apparently it can be obtained via parabolic induction from some proper parabolic subgroup. And then you can look at, say, the smallest parabolic subgroup which enables this, and automatically supercuspidal representation sigma of that Levy subgroup M, which has the property that the parabolic induction of sigma has a subquotient isomorphic to pi. And well, such a thing exists more or less by definition, and Bernstein showed that this in fact exists uniquely. So the pair M sigma is uniquely determined by an irreducible representation pi, at least uniquely up to conjugation by elements of the group G. So for a Bernstein component, you don't need one supercuspidal representation, you need a family of supercuspidal representations. Namely, you allow twists of this one supercuspidal by unramified characters of your Levy subgroup M. So in this context, a character is called unramified if it's trivial on all compact subgroups of M. Well, this gives you a family of supercuspidal representations, which I denote here by curly O. And it's somehow, yeah. And well, to this Levy subgroup M and this family of representations O, this is the data that you need to define a Bernstein component. And well, in a nutshell, the construction goes as follows. You look first at irreducible representations, and then the Bernstein component contains those irreducible representations whose supercuspidal support is of the form, well, M and something in this O that you specified. And then the second step is not only irreducible representations, but all smooth representations of G, and you take all those representations such that all the irreducible subquotients satisfy the condition that I just gave. So that is in very quickly the summary of how Bernstein defined this decomposition of the category of smooth G representations. And well, I want to understand this category rep G of S, as said before. So the prototype of such a Bernstein block is the so-called Ivohori spherical component. This is just an example. And well, how does this example look like? Many of you may have seen it. You start with an Ivohori subgroup. That's a particular compact open subgroup of G. And you look at those G representations that are generated by their I fixed vectors. And well, it turns out that this forms a Bernstein component. And the underlying supercuspidal representation here is as simple as it gets. It comes from a minimal Levy subgroup, and on this minimal Levy subgroup, the supercuspidal representation is the trivial representation. And the family of supercuspidal representations is then just the family of unramified characters of this minimal Levy subgroup. And if the group G is split, then minimal Levy subgroup just means maximal split torus. So, there are a lot of work on this, and the first results here are due to Ivohori Matsumoto, who showed that the algebra that typically describes this category, the algebra of functions on G that are bi-invariant under I, this algebra is isomorphic to an affine Hecke algebra. This was shown by Ivohori Matsumoto, and not long afterwards, or maybe around the same time, Borel showed that this category of G representations is actually equivalent to the module category of this algebra of I bi-invariant functions on G. Well, that was all, I think, in the case of F split groups, but then some 30 years later, it was realized that by Morris that this also worked for any reductive p-adic group. And in this particular example, much more is known, and in fact, all these algebras have been analyzed in a lot of detail, particularly by Kashta and Lustig, and almost everything is known about it. So this is kind of the prototype, and one expects that all other Bernstein components will have a structure which is at least vaguely similar to this. So another classical aspect of this Bernstein decomposition is the Bernstein center. And I will need that several times. So let's work it out here. So it concerns the center of this category RepGS. So well, the center of a category, well, in the case that this category is the module category of a unital algebra, then the center of the category just means the center of that algebra. So that's the way you should think of center here. And well, this center can be described in terms of two data attached to this Bernstein component. The first data is this family of supercuscular representations O, and well, this family has a natural structure of a complex algebraic torus, and one can speak of regular functions on it, and then the center consists of those regular functions which are invariant under a particular finite group, and the finite group is this constructed over here. First, you start with the normalizer of M in G, and you look at those elements in the normalizer which stabilize the set of irreducible representations O, and that gives you a finite group if you divide out M. So this is all very classical, and this gives you a nice description of the center of this category RepGS. Now, well, there's a very naive way to produce another algebra which has this center. Maybe what you can do is you take the regular functions on this complex torus O, and then you take the cross product with this finite group W of M and O. So the cross product in this context is like a semi-direct product of groups, but then, well, yeah, here it just means you take as vector spaces the tensor product. Both tensor vectors are embedded as subalgebras, but the cross relation between the two different tensor vectors takes the action of the finite group on the commutative algebra C of O into account. So it means like this: if you want to move a W over an element F prime, you have to apply the action of W on F prime. So that's a very simple kind of algebra. And well, it's also easy to see that well, at least if the action of this WMO on MO on O is free, then the center of this algebra is indeed the center here also occurring in this Bernstein theorem. And well, it's quite amazing, but it's not so far from the truth that this category RepGS is somewhat like the module category of this very simple-minded algebra, which just uses two data which you get immediately from the whole setup. Of course, it's not exactly like this, but in many cases it is, and in the general case, it's not so far from there. So now, how will I approach this? Well, I will use the approach with projective generators, I think already advocated by Bernstein a long time ago. So, well, this is usually called a pro-generator, and this is a projective generator of this category RepGS, and well, people sometimes require also that it's finitely generated, and generator means that it maps non-trivially to any non-zero object in this category. And well, there are some yoga from abstract category theory that if you have such a progenerator, then in fact the category that you start with is equivalent to the module category of the endomorphisms of this progenerator. And well, in fact, one would have the right modules of the endomorphism algebra of this progenerator. Here you see the maps. Those are pretty simple. You map rho to the G homomorphisms from the progenerator to rho, and you can also go back in a similar way. So, well, this gives you another way to look at this Bernstein block RepGS. It's the right module category of the endomorphism algebra of a progenerator capital Pi. And well, the goal of this talk will then be to investigate the structure of this endomorphism algebra of Pi, and well, to find that it's isomorphic or has a nice presentation, and then to draw further consequences. And this is not the only possible approach. A more common approach is with types in the sense of Bushnell-Kutzko. So the Ivahori group that we saw before is also the prototype of, or the typical example of a type. And well, in general, a type more or less by definition gives you a Bernstein block, namely in the sense that you have to look at the representations of G that are generated by their lambda isotypical vectors for lambda certain irreducible representation of a suitable compact open subgroup. And well, this is the approach which has been used with great success for many groups, and it automatically comes with a nice algebra already introduced by Bushnell-Kuzco, I denoted by H of G, J, and lambda, and it's by construction equivalent, or its module category is equivalent with this Bernstein block. And well, this algebra has been studied in many cases, and in many cases it turned out to be some kind of affine Hecke algebra. So what can we conclude already from this? That this G endomorphism algebra of the progenerator capital Pi will also be at least Morita equivalent to an affine Hecke algebra in many cases. So one may wonder, okay, if this approach with types is so successful, why try anything else? Well, the problem is that, well, there are two problems. The first problem is that it's not known that every Bernstein component admits a type. Well, by now, actually, this is known for a very large number of Bernstein components, and the counterexamples become rarer and rarer, but still, some groups with small characteristics or wildly ramified groups, for those it's not necessarily known that there is a type. And well, the second more serious objection is that even if you have a type, then it may not be so easy to analyze this algebra of Bushnell and Kuzco associated to it. This is the current situation for classical groups, where there are types for all Bernstein components, but it's not for all Bernstein components known what the Hecke algebra of such a type look like, in the sense that there is no good presentation for it. So, okay, so this is my motivation for studying the endomorphism algebra of such a progenerator. Okay, now I will go into more detail. So far, I've just given a very rough first version of the result, and I will first do the supercuspidal case and then the non-supercuspidal case. In the supercuspidal case, there's nothing new in what I'm going to tell here. This has been known, well, there's work of Rush from I think 2005 or something like that, but probably it was already earlier known. So that's not new, but it's very important to have a good view of this case. So the first thing that one has to look at is the tori, which underlie this Bernstein component. So I said I was looking at the family of supercuspidal representations, namely the unramified twist of one specified supercuspidal sigma. And well, more or less by definition, this means that this family of representations O is covered, or admits a covering map from the complex torus of all unramified characters, namely your tensor sigma with some unramified character. But these tori, well, or these two spaces are not necessarily the same. It is a finite covering, but it may be not a one-to-one map. You can see this already in the case of the group GL2. So for GL2, well, the space of unramified characters is just C cross, and there's a unique unramified character of order 2. And well, there exist supercuspidal representations sigma, which are invariant up to isomorphism under tensoring with this unramified character of order 2. And well, this is not a very exceptional case. If you look in the book of Bushnell and Henniar on GL2, you will see that a substantial part of the supercuspidal representations of GL2 has this property. And another substantial part of the supercuspidal representations does not have this property. So it's not exceptional. But yeah, well, this means that now there are two tori in play. This tori is torus of unramified characters, and somehow it's quotient by some subgroup. In fact, well, you can look at the number of unramified characters which stabilize sigma up to isomorphism, and this number is always finite because such an unramified character is necessarily trivial on the center of the group G. So then, well, this covering map from X and RG to O is a finite covering, and you can make it into a bijection if you divide out this finite group. And by means of this bijection, one can transport the structure of a complex algebraic variety from the space of unramified characters of G to this family of supercuspidal representations O. So from now on, O is a complex algebraic variety, and it's isomorphic as such to a torus, but it's not a group. It doesn't have a unit element and it doesn't have a multiplication. Right, okay, so far the tori. Now the progenerator. So previously I was just speaking about any progenerator, but just any in the sense of abstract nonsense from category theory won't suffice. You need a good one. This is all due to Bernstein, and well, there's a very straightforward recipe. What you do is you look at all unramified characters. So, well, the joint kernel of all unramified characters of G is the subgroup G1 generated by all compact subgroups of G. And if you divide out that group and you look at G modulo G1 and take the group algebra of that, that's in some sense as a representation of G, that's in some sense the integral of all unramified characters of G. In other words, it's some isomorphic to the ring of regular functions on the torus of unramified characters. And with this, one can construct a progenerator for any supercuspidal Bernstein block. Namely, you take a supercuspidal representation, sigma E, and you tensor E with this representation, this C of the unramified characters of G. And this is again a G representation. It's in fact the isomorphic to the induction of the representation sigma from G1 to G. And Bernstein showed that this is a progenerator of this Bernstein block in this supercuspidal case. So this is a very good progenerator. We don't need to look any further. It's as simple as it gets. And because it's so simple, it's also easy to write down at least some G endomorphisms of this progenerator. So firstly, since this algebra of rational functions on this complex torus is commutative, well, you can make it act on itself by multiplication, and that's in fact a G endomorphism. So that's just multiplication by this algebra on the second tensor factor here on this progenerator. And well, another way to produce a G endomorphism is that you start with an unramified character that stabilizes sigma up to isomorphism. And well, so then you pick an isomorphism between these two representations. You apply that isomorphism to E, and on the same time, you apply to this second tensor factor here, well, translation by chi, essentially. And that gives you also a G endomorphism of this progenerator. So that comes pretty easily. And well, actually, this generates the whole algebra of G endomorphisms of this particular progenerator. So now with this, one can also analyze the structure of this endomorphism algebra. So, well, yeah, if you have two unramified characters of G which stabilize sigma up to isomorphism, then the way in which I constructed this well, say, intertwining operator is not unique, but it's in fact unique up to scalars by a suitable application of Schur's lemma. And that means that if you have two such characters, chi and chi prime, and you compose the corresponding operators, then you get the operator associated to chi times chi prime, but maybe up to some scalar, which I denote in this particular way. And this means that these operators phi sub chi form some kind of group algebra of this finite group, but it's not entirely a group algebra. It's a group algebra twisted by a two cocycle, and this dagger or sharp or in later term natural thing is a two cocycle. And well, yeah, this formula here defines the algebra structure. It's a version, it's called a twisted group algebra. And this twisted group algebra is then embedded in the algebra of all endomorphisms of this progenerator. And well, Roche already showed that together with the multiplication operators from the commutative subalgebra X and R of G, this gives you all G endomorphisms of this generator. I don't think Roche formulated it in this way, but his results are equivalent to this statement here that the G endomorphism algebra of this progenerator for a supercuspidal Bernstein component is here isomorphic to the cross product of this algebra of regular functions on X and R G with this twisted group algebra. And here the relation or the multiplication relation in this cross product algebra is described down there. So you have both tensor factors are included as subalgebras, and the cross relation between the two takes into account how this finite group acts on this commutative algebra. And and here the action of this finite group is actually by translations on this torus X and R of G, but you have to translate by the inverse of high.
So this twisted group algebra, so the group is finite group, yes?
Yes.
So the twisted group algebra is also finite dimensional algebra, and it's not isomorphic to the group algebra?
Well, sometimes it is, sometimes it's not.
Oh.
But in this case, it's actually usually not isomorphic to the group algebra. It is always a finite dimensional semi-simple algebra, but sometimes it doesn't have, say, one-dimensional representations. So yes, in this supercuspidal case, so we have a very good description of the endomorphism algebra of this progenerator. On the other hand, we know that its module category is isomorphic to this category RepGS. And we also know what the center of this category RepGS is, because that was just the functions on this complex torus O, because in this supercuspidal case, there is no Weyl group WMO. So this commutative algebra C of O is also at least isomorphic to the center of the endomorphism algebra of this progenerator. And for similar reasons, we know what the space of irreducible representations is. It's also this complex torus O, which is in bijection with this quotient of the unramified characters of G by a finite set of unramified characters. And that's then also the irreducible representations of this endomorphism algebra of the progenerator. So that's all very good. There are a few more conclusions that can be, or a few more observations that can be made from here. So this algebra is very clear, but actually you would like it to be slightly simpler, because the center is isomorphic to the algebra of regular functions on this complex torus O, so why not take the C of O as algebra here as well? That's possible in some cases, but not in all cases. Well, or maybe not in all cases. So this is a bit of a loose end or a nuisance in this theory. This endomorphism algebra of this progenerator, which I exhibited there, is in many cases Morita equivalent with this commutative algebra of functions on this somewhat smaller torus O. But one can only show this, or at least I can only show this under an additional condition, namely if you restrict this sigma to the group G1, it should be multiplicity free. And and it is conjectured that in fact this is a condition which is always true. No counterexamples are known, but also no proof is known. And I don't know whether or not this is true in general. It would certainly make things a bit easier if it were true. But
what is always true, the assumption of the lemma or the assertion of the lemma?
Well, the lemma there is always true.
Yeah, but
the if statement is unclear.
So the multiplicity free is it's all like in all known example it is multiplicity free.
Yes, well, in all examples that I know, this restriction is multiplicity free, but it's not proven in general. And one way to reformulate this is that somehow you have this family of supercuspidal representations O, and you can you can see it in some sense as a vector bundle, or you can say the family of supercuspidal representations parameterized by these ramified characters. This is in some sense a vector bundle over this space O, and whether or not this whole algebra is somewhat simpler is in some sense equivalent to say asking whether or not this vector bundle is a trivial vector bundle. So yeah, well, okay, this issue is beyond me at the moment, and I have just proceeded with the more complicated setting. So yeah, this concludes my review of the supercuspidal case. Now let's move on to the non-supercuspidal case. So everything I did here, or yeah, most of it was motivated by work of Volker Heiermann, which worked for symplectic, orthogonal, and unitary groups. And well, so I have in some sense generalized this to arbitrary groups. So we also need a progenerator here. Fortunately, Bernstein provided us with one. And how did he do that? Well, one starts with the progenerator that we already saw in the supercuspidal case, but now we have it associated to a Levy subgroup M and some supercuspidal of M. And you use parabolic induction to produce a representation of G. And well, Bernstein showed that this is a progenerator of the Bernstein block in question. And this is not so easy. Well, it's easy to produce the representation, but to see that it is projective and to see that it is generator requires the second adjoinders relation between parabolic induction and Jaquet restriction. Well, some things that you get for free here is that you can embed this commutative algebra C of X and R of M in the endomorphisms of pi, namely just via parabolic induction. And that's very useful because this, well, this gives you a way to detect cuspidal supports of representations. So the category RepGS consists of representations whose cuspidal support certainly lies in M, O, if it has one supercuspidal support. And you can detect this via this algebra C, X, and R, M in the following way. If you have a right module for this algebra NG of pi, and this right module is, say, irreducible, and it admits a weight for this commutative subalgebra, well, then this weight high is automatically an unramified character of M. And in that case, the supercuspidal support of the associated G representation is given by sigma tensor M. So, well, in all this story, I have somehow fixed this sigma. I'm using here a fixed base point for sigma of this family of representations O. Okay, so a second ingredient that I will need are certain finite groups associated to this data M and O. So one we already saw, namely that there is a finite group of unramified characters of M that stabilize the representation sigma up to isomorphism. Another finite group comes from the Bernstein theory, namely in some sense it's a variation on the Weil group of M, and you take it by the normalizer of M in G, and then the elements that stabilize O and then divide out M. It's another finite group, and by construction, it acts naturally on this set of irreducible representations O, because, well, firstly, NG of M acts, but then M acts trivial on the irreducible representation, so you get an action on O. So yeah, I have two finite groups that are bound to play a role there. One acts on this torus and ramified character of M, another acts on this torus O. So to include them both, I lift the action on O to an action on this group of unramified characters. I'm not sure this can be done by a group-wise lifting, but at least it can be done by, well, a set-wise lifting for every element W. You can lift it to one automorphism of X and R of M. And then I combine all these automorphisms of the algebraic variety X and R of M in one group. You can do this in a canonical way. So this is a group here in the middle of this exact sequence, which contains this finite group of ramified characters, and it has a quotient, this WMO. And well, so this is a group of, say, affine transformations of the, affine transformations of this complex torus in some sense. These are transformations which do not necessarily preserve the unit element of the torus. But apart from that, they are as nice as they can get. So in an example, say you look, say group GL6, and as Levy subgroup GL2 to the power 3, and as supercuspidal representation, the tensor product of 3 copies of the same thing. Then the ramified characters form a complex torus of dimension 3. The group WMO is easily found in this example. It's just a symmetric group on 3 elements, acting by permuting the different tensor copies of tau. And well, in some cases, this new finite group which I introduced is also S3. And in other cases, it's a semi-direct product of S3 with Z modulo 2Z to the third. Namely, this second case occurs when this representation tau here is stable under twisting by an ramified character of order 2. So yeah, okay, this finite group of ramified characters forces me to introduce somewhat more complicated finite groups in the theory. Now, let me tell you something about the structure of this endomorphism algebra of pi, as far as I can now. Well, I cannot do it exactly, but it becomes easier if you relax it and replace regular functions on this complex torus X and Rm by rational functions. So that's the quotient field of this ring of regular functions. In that case, the endomorphism algebra of G or of pi tensored with these rational functions become isomorphic to a cross product of this field with a finite group, or rather the group algebra of this finite group, which I introduced on the previous sheet. And again, well, the 2 co-cycle that I had before, well, there is some 2 co-cycle involved necessarily. So yeah, if you allow rational functions on this complex torus, things are very easy. The endomorphism algebra of pi is again a simple-minded algebra, commutative algebra, semi-direct product with a twisted group algebra. So this is, well, another not so rough version anymore of the main result, which I alluded to at the start of this talk. And that's very good. But, well, in some geometric sense, in sense of representation theory, this doesn't help you much. Because if you replace this ring of rational functions by the field of rational functions, then you completely destroy the representation theory. So from this statement, this isomorphism, you cannot draw many consequences about representation theory. Well, that's life. So to draw consequences about representation theory, further analysis is required.
So in the case when M is, say, the torus, then the cocycle is have to be trivial?
I don't think so.
So the cocycle from okay, maybe if this finite group, the first finite group is trivial, then this cocycle is also trivial, or this cocycle is
no, not even then. So inside this finite group which I have here, there is always a while group of some root system, and the cocycle is trivial on this while group. But if there's further contribution to this finite group, then maybe I have a non-trivial cocycle. I know examples where this cocycle is non-trivial.
So the cocycle is trivial on the while group?
Yes.
So if everything is just a while group, if you don't have this finite group of characters, then it has to be trivial, yes?
That's right, that's true. Yes.
So it means that in the Iwahori case, it also has to be trivial.
Then it's trivial, yes.
So in the Iwahori case, it is true that if you pass to the rational function, then the Iwahori-Heck algebra just becomes a group algebra of the affine wave group?
Yes. That's true. And it's actually easy to show if you just look at an affine Heck algebra in terms of representation. Okay, now let me show you why it's easier to start to involve these rational functions. This can already be seen in the simplest example, SL2, where you take as Bernstein component, well, the simplest component coming from the trivial representation of the maximal torus. In this case, the finite group has just 2 elements with a standard reflection. And well, yeah, in this case, there's also an intertwining operator from one principal series representation with a character chi to another principal series representation with a character chi inverse. And you can get this intertwining operation by, well, in a suitable model, integrating a function on G on a root subgroup. And this is an integral over a non-compact group. And this integral is in general not convergent, but nevertheless, you can make sense of it. And if you make sense of it, it turns out to be a rational function of the variable chi. But it's a rational function which has singularities. And yeah, well, to relate this to the previous sheet, you can compose this intertwining operator with another kind of innocent operator, and then you can produce an object, say, which I call here J S alpha, which does lie in this, well, this intertwining, this endomorphism algebra with rational functions. And this J then squares to 1, and it somehow reflects that you do high to high inverse on the torus. And that's how you can arrive at this description of the endomorphism algebra of the progenerator with rational functions. But then this normalized intertwining operator JS alpha has singularities, and the singularities occur at particular points, namely where the character is, well, say the Q, where Q is the number of elements of the residue field, or it's Q inverse. And well, these singularities cannot be removed so easily. So that the operator I also has singularities. The operator I as alpha has singularities when chi is 1 or minus 1. If you normalize those away, then you come up with this operator J, but that has other singularities. It's not possible to normalize them all away. So this explains why it's easier to work with rational functions than with regular functions on this torus. But okay, now I want to get a better description of this endomorphism algebra with regular functions, which allows me to say something about representations. And this goes via Hecke algebras. Well, it's too ambitious to describe everything in one stroke with an affine Hecke algebra. This can be done for the a priori spherical component, but not in general. At least I do not know how to do it in general. But well, we can do it if we are a bit more flexible. So first, let me say what kind of affine Hecke algebra I mean. I will take a somewhat, well, uncommon construction. I make this algebra by deforming a simple-minded algebra. So I start with this cross-product algebra of a commutative algebra, functions on a torus O, with this finite group from the Bernstein theory. And well, inside this finite group WMO, there's a reflection subgroup or a while group associated to a certain root system. And now we must modify some things. Well, first modification is that this group algebra of the finite group WMO must be modified by a certain 2 co-cycle. So you make out of it a twisted group algebra, and this 2 co-cycle will be trivial on this while group inside there, but maybe non-trivial in general. The second modification is that for the simple reflection of this while subgroup, you have the relation S alpha plus 1 times S alpha minus 1 in the group algebra, and these must be replaced by introducing some Q parameters, and then you get a relation like this. Ts alpha plus 1 times Ts alpha minus Q is 0. For a suitable Q, which is Q number of elements of the residue field to some power, and this Q is to be determined later. And well, if you do that, then to make an algebra out of this, you must also change the remaining relations in some way. I will not go into the details there, but it can be done in a way which produces an associative algebra. And well, this is a version of an affine Hecke algebra, and then the construction is such that this commutative algebra C of O is still inside there as a subalgebra. This finite group algebra C of WMO is replaced by, well, on the one hand, a Hecke algebra of a finite while group, and on the other hand, a twisted group algebra of some finite R group. And well, these are all together in one algebra, which I call here H tilde of O. And this is not the standard way to look at an affine Hecke algebra, but there is a proper affine Hecke algebra inside there. So, well, it's too ambitious to describe the whole category RepGS in these terms, but it can be done if you restrict to, well, to certain subcategories, or well, rather you restrict to a set of representations where you don't have all possible supercuspidal supports, but only supercuspidal supports which land in a certain part of this torus X and R of M. So for this, you specify a subset of this torus X and R of M. It should be a subset which is invariant under this finite W group. And you look only at the representations whose supercuspidal support is of the form sigma tensor chi with chi in this set U. And I will take a U of a particular form. Well, it's somehow I take this torus, I take a polar decomposition. It's a complex torus, so I have in some sense a unitary direction there from unitary and ramified characters, and I have a positive direction from positive valued characters. And the u that I take is a ray in the positive direction. So meaning that here I have the positive direction, x and r plus of m. I fix one unitary character u. I take the whole ray from u extending in the positive direction, and then I must make it invariant under this W group, so I multiply it with that. This is the set u of well, say, supercuspidal supports that I want to use. And well, if you restrict to representations whose supercuspidal support lies over there, then things become a lot easier. Somehow, well, you don't see the entire Bernstein component anymore, but the algebras that you need for that are a lot easier. And in particular, this finite group of unramified characters is now superfluous, and we can maneuver it away and make easier algebras. So this brings me to the main result, which I can now formulate more precisely. So recall we started with a supercuspidal representation sigma of a Levy subgroup M. We looked at the family of all unramified twists of sigma. There was a family of O of supercuspidal representations. That gave rise to a Bernstein component, RepGS. And for this Bernstein component, we had a progenerator, capital Pi, and then we wanted to analyze the Bernstein component by looking at the G and the morphism algebra of Pi. And it will be analyzed in terms of an affine Hecke algebra H tilde of O, which I constructed by modifying this simple-minded algebra, and I modified it basically by introducing some Q parameters in the relations that evolve the simple reflections, which lie in this group WMO. And well, then I analyzed this by restricting to say a ray U in the complex torus X and Rm. And well, the statement is there that if you go look not at this entire Bernstein component, but at those representations in the Bernstein component which have finite length and whose supercuspidal support is contained in the subset U, or here U tilde, which I specified, then this algebra or this set category of representations can be described, well, first as a category of representations of the endomorphism algebra of this progenerator, because, well, we already knew that RepGS was equivalent to the category of right modules of ng pi. But then now it can also be described as a category of modules of this affine Hecke algebra, which I introduced somehow manually. And well, so this whole business requires that you can break down representations according to their weights for commutative subalgebras or according to their supercuspidal supports. And this works well for finite length representations, but it doesn't work so well for arbitrary representations. So that's why in this theorem, everything has to be restricted to finite length representations. But okay, for those finite length representations, it works out very well. And well, so this is somehow, in this theorem, maybe one should say that the unitary and ramified character U is specified here in advance, and possibly this affine Hecke algebra depends on the U. But it turns out it depends only very weakly on the U. So there's a stronger version of this theorem, but that's somehow conditional on some technical nuisance which I have not been able to prove in general. Namely, under a mild condition, this category of RepGS, and there the finite length representations, is equivalent to the module category of this affine Hecke algebra H tilde of O, and also the finite length modules there. So this is a generalization, say, of the equivalence found by Borel for the Ivory spherical component, or the equivalences which are known for all Bernstein blocks in the representation geotheory of GLN. And well, this is going to hold most probably for every Bernstein component in every reductive p-adic group. There's here a condition on this 2-co cycle, but I think this condition is always fulfilled. And even if the condition doesn't hold, then there's a more cumbersome formulation of this corollary, which is slightly weaker, but not much weaker, but it's so much more cumbersome to formulate that I'm not going to phrase it here. So the upshot is that this Bernstein block is always equivalent to the module category, at least for finite length modules of an affine Hecke algebra. And well, there's extras to this. Well, contained in this whole setup is that this business is compatible with parabolic induction. An affine Hecke algebra admits parabolic subalgebras, and that's compatible more or less by construction. And well, further analysis of the situation allows one to show that in fact this equivalence of categories will also map tempered representations of G to tempered representations of an affine Hecke algebra. And you can also say something about square integrable representations of G in terms of, say, discrete series of affine Hecke algebras, for those of you who know how those are defined. So this equivalence of categories actually preserves a lot. Also, let me recall that this equivalence of categories in some sense preserves the cuspidal supports, because for RepGS we have a cuspidal support map, and for this affine Hecke algebra there's also some kind of cuspidal support map. It just means restriction to the large commutative subalgebra of this affine Hecke algebra. So, well, that's very nice. We have now managed to translate a Bernstein block to the module category of an affine Hecke algebra.
There seems to be a question. At least Dan Cibataro raises a blue hand, and I'm not entirely sure.
Maybe he can unmute himself.
Yeah, I didn't know how it works. Can I ask a couple of questions? So the first question about your main theorem here,
Yes.
Should I think about this fixing U sort of like a reduction to the graded Hecke algebra? So this is very similar
Yes.
to
Yeah,
what happens.
that's right. That's how I prove it, in fact, by reducing
okay.
to some graded Hecke algebra.
Okay, good. And the other question, the parameters lambda alpha, those
Yes.
are related to poles of these intertwining
Exactly.
operators.
They come precisely from the poles of these intertwining operators.
And so in complete generality, they're not known. Is that correct?
Well, no, I don't. Unfortunately, this description of these intertwining operators makes it pretty difficult to find a concrete formula for the poles or the zeros of these intertwining operators, at least
But
in general.
Can you at least say that if the supercuspidal is generic, then they're all one or something? Or using maybe Shahidi's results?
Well, I'm not sure of that. Well, I know that if there is a type around, then you can detect these parameters also in terms of the Hecke algebra of this type. And by means of those terms, one can find these parameters in many cases. I don't know whether one can detect them also with this Shahidi method. I looked at it, but I found it not so easy to do it in that way.
Okay, thank you.
Okay, now let me try to draw consequences from this using what's known about Hecke algebras. Well, this may not be so well known to everybody, but in fact, the representation theory of affine Hecke algebras is very well advanced, and one can say that the irreducible representations are completely classified in some way, but well, the way to classify them is involved. So I will not discuss that in detail. I will just draw consequences. So one way to phrase the classification or to reformulate it is to go via the version of an affine Hecke algebra where the parameter Q is manually replaced by 1. That results in an easier algebra. So if you take the affine Hecke algebra that I had before and always replace all Q's by 1, then you get back the algebra that I started with. Namely, you start with the commutative algebra C of O and you twist it, or you take the cross product with the finite group algebra of this group WMO, and well, there's also still a co-cycle involved because it's not removed by setting Q as 1. And well, this kind of algebra is easy. Actually, yesterday we saw in the talk of Alexander Avkutsidis very similar algebras of the type commutative algebra semi-direct product with compact group, and Mackey theory, or in this case Clifford theory, gives you a pretty direct construction of the irreducible representations of such an algebra. And well, this can be applied here to some kind of comparison result between the representations in this Bernstein component, which are irreducible, and the representations of the affine Hecke algebra with Q replaced by 1. And this works best for tempered representations. So let me formulate it there. So now I start with a supercuspidal representation and I tensor it with a ramified character such that the result is not only supercuspidal but also unitary and hence also tempered. And in this case, well, so the category of representations in RepGS which are tempered and have irreducible and have supercuspidal support in this particular ray in this complex torus is equivalent to a particular set of irreducible representations of this affine Hecke algebra with a similar condition on the weights for this commutative subalgebra. That's already from the previous slides. But well, by setting the parameter q equal to 1, one transforms this to a set of irreducible representations of a simpler algebra, namely this algebra where you don't see a q anymore. It's not really an affine Hecke algebra anymore. And it's a representation of this algebra which are still tempered, but now the weight of this representation is only in this, it's only become this one particular sigma tensor U. And yes, well, via the Clifford or Mackey classification of irreducible representations, this is a very explicit set of representations, namely it's in bijection with the irreducible representations of this finite group algebra of this, the stabilizer of this sigma tensor U in this finite group WMO. But well, you're still left with the remnants of a certain 2-cos cycle, at least conceivably. In some cases, you are still left with that. So, well, this is already a kind of classification of irreducible tempered representations. And well, it relates very well to the talk yesterday by Alexandre, where he had the relation between the tempered irreducible representations of a real reductive group and the tempered irreducible representations of its Cartan motion group. But in the p-adic world, there's more. You can, if you know something about tempered representations, then you can use the Langlands classification to create a fact to promote this to a statement about all irreducible representations. And that's on the next slide. Namely, well, there's a canonical way to enhance the previous result, and then it becomes a bijection between all irreducible representations in this particular Bernstein component and all irreducible representations of the algebra that I had on the previous slide, CO as cross product with W group algebra of WMO with a certain 2-cos cycle. Well, this 2-cos cycle is subject to a mild technical nuisance. If you don't like that, you can go to a larger algebra where you have not this complex torus O, but the complex torus of all ramified characters of M, and you have a larger finite group and a 2-cos cycle, but this again, now this 2-cos cycle is there unconditionally, and then it's also equivalent. The irreducible representations of S are also, well, canonically in fact in bijection with the irreducible representations of this algebra. I say here canonical with a question mark because it's work in progress, but by now I have convinced myself that this is actually really canonical. And well, yeah, with means of this Mackey theory, you can parameterize the irreducible representations of these two algebras here in the middle in another way. There are two parameters here. One parameter lives in this torus O, and one parameter is an irreducible representation of the stabilizer group in WMO of this, well, the first parameter sigma prime, but then the stabilizer group must be replaced by a twisted group algebra of that. And to get all irreducible representations, one must still divide out the entire group WMO. This is a kind of combinatorial or more geometric description. If you use this description, well, then you come back to something which was already, well, studied some 10 years ago by my co-workers, Annemarie Aubert, Paul Baum, and Roger Plyman, and it was called a twisted extended quotient. So there's now a twisted extended quotient of a complex torus O, by a finite group WMO, which comes directly from the Bernstein theory, and the twist refers to some 2-co cycle, which is still involved there. So in total, this produces a bijection between the irreducible representations in an arbitrary Bernstein component for an arbitrary reductive p-adic group, and some other object here, which comes in terms of pretty simple data attached to the Bernstein component. Namely, the data are just the complex variety O and the finite group WMO. Those are the simple data and the somewhat, well, intractable datum of a 2-co cycle. And well, yeah, this is the description, and this is a version of a conjecture, well, by Baum, Kleiman, Aubert, and me from some 10 years ago. But now we have it in complete generality. Okay, I see that I'm over time, but I'm also at the last slide, which just summarizes what I told you here. So we looked at an arbitrary Bernstein component of some reductive p-adic group, and well, we showed that the category of finite length representations there is equivalent with the category of finite length representations of some extended version of an affine Hecke algebra. And this affine Hecke algebra, I didn't describe it too explicitly, but I described explicitly what would happen to it if you would replace Q by 1 in this affine Hecke algebra. And that what gives you this rather simple form of an algebra. And if you're not satisfied with that, well, you can say that if you relax your conditions, you can say relax by replacing rational functions on the torus of unramified characters of M by regular functions on this torus of unramified characters. Then this RepGS becomes equivalent to the category of right modules of this algebra here, also a kind of cross product algebra, but then you must think of it as somehow with rational functions. And it also, RepG also becomes equivalent to the module category of this algebras if you are content with just looking at a set of irreducible representations. Yeah, so in these are the ways in which I make the claim which I had at the very first slide of my talk precise. And well, of course, this doesn't solve everything because there are various loose ends. For example, and which Dan asked, the parameters Q to the power lambda alpha. I don't know how to describe them. Another problem here is, well, what to do with unitary representations. Can you also see it in these terms? I don't know that. And a third open problem is, well, how on earth do you get a good description of this 2-co cycle if it's non-trivial? And I know that there are certain cases where it is non-trivial, but at the moment, I don't know a good approach to, to making that more explicit. So, well, yeah, those are my open problems. If you have questions, then please ask them now. And if you don't, in any case, thank you for your attention.
So I do think I have a question about the Caspidal case. I thought I understand it, and now I'm starting to have doubts.
Okay.
So you said that, okay, you said there is certain vector bundle which might be trivial and might be not.
Yes.
And then you consider it. So this is vector bundle over the center, like over the smaller toes, all
Yes.
twisted.
Yes.
And over each, and then you take endomorphism of this vector bundle.
Yeah, that's a way to get this endomorphism algebra of the progenerator that we looked at.
So over each point, you do your algebra does look like endomorphism algebra of a finite-dimensional vector space. Yes.
Yeah, I think you can put it like that. Well, yeah.
So this would make me confused. So this, on the other hand, you say it's tensor product of
maybe
polynomial.
maybe you're right. Maybe this description of a vector bundle is more an analogy than that it's actually precise. I think.
Oh.
Yeah,
But it is so over one point in the Bernstein center, the category is just vect. Yes, it's nothing.
that's true. Yeah, yeah.
So I don't understand the thing about, so you say you take a tensor product, or not a tensor product, you take like this semi-direct product with
Yes.
finite dimensional algebra, but this finite dimensional algebra is, so it's semi-simple algebra,
Yes.
but it's not group algebra of
No, well,
this
typically what it can be is like, say, the algebra of, say, 3 times 3 matrices. That can happen here.
Mm.
So then it means that on each point of the center you would have a 3-dimensional representation.
And the dimension of this small algebra is the size of the stabilizer of this of a representation row.
Well, that's no, not necessarily. Well, it is related to the multiplicity of the restriction of your supercuspidal representation to the group G1 in that case.
Okay.
Um,
And my second question, so when you state your equivalence of categories, you restrict it to finite length representations.
yes.
This is crucial or it's technical?
Yeah, it's technical. The method which I use works only for finite length representations. But yes, well, I don't know whether the results that I get are also valid without restricting to finite length. In many cases, they are, for sure. If you are in the case where you have a type and it's also equivalent to the Hecke algebra of a type, then certainly it's not necessary to restrict to finite length representations. But in general, I don't know.
Okay. Thank you.
Martin, can I ask a small question?
Sure.
First, thanks very much for your talk. The last year has shown me how important that kind of result is. I wonder about what your main result says about the reducibility of induced representations. So, for instance, for tempered representations, how does the Knapstein R group enter at some point?
Yes, well, certainly this Knapstein R group is also inside there. So if you take, well, some point of this torus O, and you look at the, say, well, so some point, say, T of this torus O, and you look at the stabilizer of T in this group WMO, then this stabilizer has the structure that it contains a Weil group, and it is a semi-direct product of a certain Weil group with a certain R group. And well, that is in fact, again, this Knapstein R group. You can see that it works out that way.
Yes.
So that, and also this theory of Knapstein, which described the structure of say, a tempered parabolically induced representation in terms of R groups and intertwining operators, that's also present here.
Yes, but somehow, in a sense, you have the representations of the full stabilizer of your point, which you got T earlier, rather than just the representations of the Weil group, which seem to occur in.
Yes, well, if you look at the algebras here, like this algebra C of O cross product with CWMO, that's certainly right. But yes, well, it somehow means that if you take this operation of replacing Q by 1, a lot of things change.
Oh, right.
And in particular, this Knapstein theory, where in this Knapstein theory, the small Weil group associated to a particular point somehow becomes trivial,
right.
And you don't see it anymore. But in this algebra, that doesn't hold anymore, and that's somehow because it was lost if you replace Q by 1.
Okay, I understand much better. It's the change of Q that does the trick. Yeah. Thank you.
Are there any other questions? If not, then thank you very much, Martin, for a very nice talk.
Thank you.
So let's have a 10-minute break and then we continue for the next talk at 20 past.
Okay.
Thank you.
I think so.
Aaron, would you like to check whether your share screen is working and so on?
Yeah, good suggestion. Let me try that.
I'm missing the bottom bit.
Let me try full screen.
That seems better. Yeah.
Okay, great.
Okay, very nice.
So I'll go back to full screen when we start.
T'as rien compris. Faut que tu te reposes.
So maybe we continue. So the second and last speaker of this afternoon or morning, or depending on where you are, let's say today, is Aaron Pollack with special automorphic form on exceptional groups. So please.
Okay, well, thank you for the introduction. It's a pleasure to be speaking here. So hopefully everything looks right. This is my first time giving one of these Zoom conference talks, so hopefully everything goes smoothly. So yeah, special automorphic forms on exceptional groups. So let me say sort of right off the bat what special means in this context. So what that means is that I'm looking at automorphic representations on certain exceptional groups for which the infinite component is a particular type of discrete series. So the talk is about an analog of Siegel modular forms for certain exceptional algebraic groups. So, excuse me, I'm going to begin by sort of reviewing Siegel modular forms and their properties, and then move on to the exceptional groups. So the things I want to highlight about, hopefully everything is working okay here. The things I want to sort of highlight about the Siegel modular forms are that they're sort of special automorphic forms for the symplectic group SP2N, and they have a robust Fourier expansion, which I'll review, and they're sort of closely connected to arithmetic. And the modular forms on the exceptional groups have at least some of these properties. So the whole theory was initiated by Dick Gross and Nolan Wallach, and it's been studied by Wee-Tek Gan, Dick Gross, and Gordon Savin, Loki and Weissman, and the speaker from sort of different perspectives. So what one gets are special automorphic forms, the groups G2, spin 8, F4, the split versions of those groups, and the exceptional groups E6, E7, and E8, whose row rank is 4. So that's what that notation means, E6, 4, E7, 4, E8, 4. And the theorems that I'll discuss, so the first result is that these special automorphic forms, they have a sort of robust Fourier expansion, which is similar to the Fourier expansion of the Siegel modular forms. And then from that Fourier expansion, one can define a notion of, a good notion of Fourier coefficients. And the second result is sort of a collection of a few different results, which are examples of modular forms that are arithmetic in the sense that they have Fourier coefficients, which are all in Q bar, the algebraic closure of Q. Okay, so Siegel modular forms. So recall the complected group SP2N, so just a subgroup of GL2N that fixes invariant, fixes a non-degenerate symplectic form, and it's given matrices in this form. So it fixes, transpose G times 0, 1, minus 1, 0. G is equal to that matrix. The maximal compact subgroup, which I'll need, of the symplectic group is the unitary group UN, which is embedded in SP2N in this form, and N by N block form, the matrices AB minus BA. And then what does the symmetric space look like for SP2N? So denote by SN, the N by N symmetric matrices. And then the Siegel upper half space is identified with a symmetric space for SP2N. And it looks as follows. So denote by HN, the Siegel upper half space. So these are the N by N complex matrices, X plus IY, where X and Y are symmetric matrices and Y is positive definite. So then this is, like I said, this is identified with symmetric space, SP2NR mod UN. So SP2NRX on HN, this Siegel upper half space by GZ is AZ plus B times CZ plus D inverse, if G is ABCD in N by N block form. And then the stabilizer of the element I times the identity for this action is the compact group UN embedded in SP2N. So that's the symmetric space. So now for the Siegel modular forms of some weight L. So L is some integer, positive integer, and you consider the holomorphic functions f on the Siegel upper half space that satisfy the functional equation f of az plus b, cz plus d inverse is determinant cz plus d to the L times f of z for all a, b, c, d and some congruent subgroup gamma of sp2n. So that's the definition, and they have a robust Fourier expansion, which maybe is hopefully familiar with most people, but maybe not to everyone. So if z is your element in the Siegel upper half space, then you have this Fourier expansion. F of z is a sum af of t, so those are complex numbers, times e to the 2 pi I trace tz. So T is an n by n symmetric matrix, which is positive semi-definite. So T times Z is an n by n matrix. You can take its trace, and then you could exponentiate that. From the point of group theory, which I'll mention on the next slide, this is basically a Fourier expansion along the Siegel parabolic subgroup of sp2n. So just to say some basic things, so if n is 1, so then sp2n is SL2. So these are, of course, the classical modular forms for SL2. And more generally, for general n, if you have a Siegel modular form of weight L, you can consider it as a section of some holomorphic line bundle, which I've written here is script L to the L, a global section of a holomorphic line bundle on Hn mod gamma. So here gamma is again this congruent subgroup for which F is sort of semi-invariant. So this is the classical definition. So let me review what they look like automorphically. So automorphically, you've got a function phi from sp2n to the dells on sp2nq that's complex valued. It satisfies two properties. First is a k equivariance property for the right regular action of k on sp2n. So namely denote by z this the determinant map from un to u1 sitting inside of C cross. So then phi of gk is z of k to the minus L phi of g for all k in un and g in sp2n of the adells. So this is telling you the weight, this k action from un. And then the holomorphy becomes the fact that phi is annihilated by a first order linear differential operator, which I've written here is script d sub CRL. So the CR is for the Cauchy-Riemann equation. So in other words, when you take phi and produce a function f associated to phi on the Siegel upper half space, you want that function to be annihilated by the Cauchy-Riemann operator. And so that turns into a differential equation satisfied by phi. And then from the point of view of automorphic representations, the Siegel modular forms are just, you're looking at those automorphic representations pi, for which the infinite component pi infinity is a holomorphic discrete series representation. So because it came up yesterday, let me mention right away that, before I mention the Fourier expansion here, that these discrete series, these holomorphic discrete series are not generic. They don't have a functional, sort of a unipotent functional appropriate one for the maximal unipotent subgroup of sp2n. And so when one's looking for a Fourier expansion, you can't, one can't do a Whittaker expansion, but instead you look for a Fourier expansion along a maximal parabolic subgroup as opposed to a minimal one. So you take the so-called Siegel parabolic subgroup. So that's the it's upper triangular and n by n block form. And the Fourier expansion, the sort of robust Fourier expansion that I have in the previous slide here, in terms of group theory, looks as follows. So you plug in the matrices 1x, 0, 1, and y to the 1/2, 0, 0, y to the minus 1/2. So x and y are n by n symmetric matrices, y is positive definite, and the Fourier expansion of these phis looks as follows. So you have an e to the 2 pi trace tx, so that's sort of there by fiat. You're Fourier expanding along this upper, unipotent radical of the Siegel parabolic, And then the fact that your function phi satisfies the Cauchy-Riemann equations forces two other things to happen. So it forces that once you look at the coefficient of e to the 2 pi I trace tx, what's multiplying that is this e to the minus 2 pi trace 2y. So y is here from the levy of the Ziegler parabolic. And moreover, the sum is only over positive semi-definite matrices T. So those two things are sort of forced on you by the fact that phi satisfies these Cauchy-Riemann equations. Okay. So more generally, if you have a reductive Q group G and a maximal compact subgroup K inside the real points, you can look at the case when G of R mod K has a structure of a Hermitian tube domain. So these, there's a finite list of such groups, and up to isogeny, you've got sp2n, unn, so2n, and a form of E7 that has real rank 3. And then there's also like a form of E6, which has a Hermitian structure, but it's not a Hermitian tube structure. So that's why I didn't put it in this list. So for these groups, you've got a good notion of modular forms. And I put that in quotes. So what do I mean by that? It's just automorphic forms on G of the Adels that give rise to sections of holomorphic line bundles on the symmetric space, which you can talk about because we're assuming that the symmetric space for now has a Hermitian tube structure. And there's sort of two important properties of these modular forms. So the first is that they have a robust notion of the Fourier expansion, sort of generalizing this Fourier expansion on this slide or this one on this slide here. And moreover, and this is maybe the more interesting part, at least to me, is that they're sort of closely connected to arithmetic. So in various ways, and one way in which they're connected to arithmetic is that you can take a basis of the space of these modular forms, and for every element in the basis, all of the Fourier coefficients are in the algebraic closure of Q. Okay. And again, these Fourier coefficients, they're these AF of T's in this expansion here. And so I wanted to mention just a few, before moving on, I wanted to mention just a few sort of useful properties of holomorphic modular forms. You know, it's sort of, everyone does automorphic representations nowadays, or a lot of people just work on automorphic representations nowadays. So I wanted to, and so maybe holomorphic modular forms are in the rearview mirror a little bit. So I wanted to mention a few, you know, important uses of them. So one is just sort of classical generating functions. So you have data functions, for example, on GL2 or sp2n, for which the Fourier coefficients are representation numbers of quadratic forms. That's something you can do because you have this sort of nice Fourier expansion. You can sometimes construct cusp forms more easily. So namely, I'm thinking of the Akeda lift here and its generalizations. There's work on, it's much easier to do sort of work on L values. So you can talk about applications to Delen's conjecture and p-adic interpolation of L values, so both things which are easier from the holomorphic point of view and much more accessible. And then finally, just the last thing I sort of wanted to type down here, there's sort of geometric generating functions, which goes into the name of the Kudla program. So you have sort of generating functions for which the elements that the series that one is generating, the coefficients are like cohomology classes on, for example, for locally symmetric spaces associated to orthogonal groups. So I'm thinking there of work of Kudla and Milson. So in all these cases, there's sort of, it's much easier to do stuff and they're much more closely connected to holomorphic modular forms. So that's just sort of an aside. That's my review of the Ziegler modular forms and their generalizations to tube domains. So now I want to get into exceptional groups. So starting off with, if you take a group G, the symmetric space G of R by K is usually not Hermitian. So what can one do in that case if one wants to study sort of interesting automorphic forms? Well, if you're working with classical groups, the first thing you could do is you could fix the Dinkin type and vary the real form of the group. So, for example, if you're in type A, you can look at the unitary groups, UPQ, or if you want to do tube domains, UNN. In types B and D, you can look at SO2N, so signature 2N quadratic forms, and then those have a Hermitian symmetric space. But if you take other signatures, you won't have a Hermitian symmetric space. And in type C, you can look at SP2N. So in all those cases, you can sort of vary the real form by fixing the Dinkin type and get something Hermitian. But for exceptional groups, you can't do that. So for example, if G is of type G2, F4, or E8, there's no real form for which the G mod K is Hermitian, for which the symmetric space is Hermitian. So for E6 and E7, you can get a real form for which the symmetric space is Hermitian, but not for G2, F4, or E8. So that leads to the question, I guess, at least given the fact that it'll have an interesting answer, it leads to the following question. So given an exceptional Dinkin type, can you single out a class of special automorphic forms that are sort of similar to the holomorphic modular forms on tube domains? So that's the question that motivates this talk, and a lot of this stuff I've been thinking about for the past couple of years. So one answer to that question, and this is motivated by, and sort of motivated and paraphrasing some work of Gross and Wallach, is that you can do the following thing. So you could first look at a group G for which G of R possesses discrete series representations. So that's that happens when you have this equal rank condition, rank K equal to rank G. You could furthermore look at automorphic representations for which the infinite component is a discrete series. And so now you've singled out some nice automorphic representations that are cohomological, at least if you're, yeah, so those are cohomological. And then you can restrict further, so not just take pi infinity to be a discrete series, but look at those pi infinity which have the smallest possible Gelfand-Kirchhoff dimension among the discrete series, and then maybe moreover, the simplest possible sort of families of minimal K types. So now you've really singled out a class of automorphic representations, and it turns out, well, it's just one thing one could do, and it turns out, at least in some cases that I'll talk about, you can really get something, or appear to get something quite interesting. Okay, so so what are precisely the reductive groups that I'll be talking about? So in the exceptional case, like I mentioned, you have G2 or F4, or you can also say spin 8, the split forms of those groups, and forms of E6, E7, and E8 with real rank 4. And there's and if you don't like exceptional groups, you can think for the whole talk, you can mostly focus in on the case of G isogenous to SO4N with N at least 3. So these, all of these groups that I've written here, they sort of behave very similarly, and one can prove results uniformly between, some results uniformly between these groups. Okay, so it'll be very important for me to single out what happens with the maximal compact subgroup for all of these groups. So let me tell you what it is for all of these groups. So suppose G is of the above type, and it's adjoint, and K denotes the maximal compact subgroup of the real points. Then in all these cases, K is of the form SU2 times some auxiliary group L, monodiagonal mu2. So you can ignore the mu2 for now if you want, but it'll come back later. And so L in these cases, of course, it depends on the group. So for example, on F4, L is the compact form of SP6. On E8, L is the compact form of E7. On G2, K is SU2 times SU2, monodiagonal mu2. And this, the first SU2, the one that I'm sort of singling out here, is the so-called long root SU2. So a long root of, over C, a long root of the of G2 sits inside this SU2. But in all these cases, you have a normal SU2. So this SU2 here. And I mentioned that to sort of compare it with the Hermitian case. So if you have a group H that has a Hermitian symmetric space, then the maximum compact subgroup has a normal U1. And this U1 is sort of precisely the thing giving the the complex structure on the symmetric space. So this normal SU2 gives what's called a quaternionic structure on the symmetric space. These groups are frequently called quaternionic groups. And the discrete series that I'll mention later, quaternionic discrete series. Okay, so here's the quaternionic discrete series. So Gross and Wallach singled out this sort of family of so-called quaternionic discrete series on the above groups. And it'll come back frequently, so let me give them a name. So fix an integer L, at least one, and doing so, there's a discrete series, at least if L is sufficiently large, there's a discrete series pi sub L on a group, one of these groups G above, or any of these groups G above, whose minimal K type is the 2L symmetric power of the standard representation of SU2 and the trivial representation of L. So I call this V sub L. It'll appear throughout the talk. So let me just mention again, because of this diagonal mu2, that's really here in dividing out SU2 times L in the definition of K here, and this equality for K, you really need an even symmetric power of the standard representation of SU2. So that's why this VL has a 2L symmetric power here. Okay. So, Gangos and Savin used these representations to define a modular form. So they were most interested in G2, but sort of one could take the following definition. So take the space of automorphic forms on your group G. So again, G is any one of these groups, whatever is your favorite group, whether it's G2 or XO44 or E8 or what have you. And take a GR equivariant homomorphism from pi L into the space of automorphic forms on G. So then you could call that such a map a modular form of weight L. There's an equivalent definition, or essentially equivalent, which I prefer to use, which is as follows. So take an automorphic function f, capital F, on G of the Adels by G of Q, and again, have your integer L, at least one that's fixed. Then you could look at functions capital F that are valued in this dual of VL. So VL is again this 2L symmetric power, and satisfy two properties, sort of completely analogous with the Siegel modular case. So let me remind you quickly what I wrote down here. So Siegel modular forms, if you write them sort of automorphically, there's a K equivariance condition and a differential operator condition. So I'm just going to say sort of the completely analogous thing here. So namely, you insist that f of GK is K inverse applied to f of G for all G and G of the Adels and K in this maximal complex subgroup. So you have the right regular action of K on the left-hand side here, and the action of K on this VL on the right-hand side of this equality. So that's the simple condition. And the interesting condition is that you say F is a modular form of weight L if it satisfies this, and it's annihilated by a certain differential operator DL, which I'm going to tell you more about on the next slide. Okay. So what is this differential operator DL? So it's basically a way of saying that it's a way of reformulating the fact that this VL is going to be some minimal K type in the GK module generated by F. That's really what it is, but let me just, for concreteness, tell you what the operator DL is, what the differential operator is. So it's defined easily in terms of the Cartan involution. So take your Cartan involution on G associated to the maximal complex subgroup K. So you have a decomposition, G is K plus P, and fix a basis, any basis, X sub I of P, and Xi star, the dual basis of P dual. And then you can do two things. So the first thing you could do is write down a formal differential operator, which I've called here d tilde, where you just apply the right regular action of the xi's to f, and you tensor with xi star in p dual. So this is an operator that's valued in the dual of VL tensor p dual. So just some sort of formal operator. It doesn't really kill anything. Nothing's really annihilated by it. But you can do a little bit more to get something interesting. So namely, P as a representation of K, it's you have a V2 here, the standard representation of SU2, and you have a certain irreducible representation W of L. So it's just a simple tensor product. So when you take VL dual tensor P dual, I should say P dual, but it doesn't really matter. You get two copies, you get a sim to two different irreducible representations. So just using the representation theory of SU2, you get a 2L minus 1 symmetric power V2 tensor W, and a copy of the representation sim to the 2L plus 1 V2 tensor W. And now you can get an interesting operator by first taking d tilde, which gives you something valued in this direct sum, and then project onto the first component, the smaller irreducible representation. And so the operator DL is just the composition of those two. So that's what it is, very explicitly. And just to reiterate, it's just sort of another way of saying that the GK module generated by capital F, it contains the representation VL, but it does not contain this representation, this sort of smaller representation in terms of SU2s, the SU2 representation theory. Okay. So that's the definition of the modular forms. So the first result that I want to talk about is the Fourier expansion. So what does that look like? So what you do is you take a maximal parabolic subgroup inside your group G, which is the Heisenberg parabola. And I've just written here for all of the different cases what parabolic I'm referring to. So the notation is P is my Heisenberg parabola. It is Levy H, which I'll tell you why I call it H in a second, and unipotent radical N. And the unipotent radical N is a two-step unipotent. In all of these cases, sort of everything works uniformly for all of these different groups. It's two-step in all of these cases. Z here is its center, it's one-dimensional, and then the quotient N mod Z is abelian, and I've written W for that quotient. So for example, for SO4N, P is the parabolic with Levy GL2 times SO2 N minus 2, and N mod Z is the representation, the two-dimensional representation of GL2 times the n-dimensional representation of SO2 N minus 2. For G2, this is the parabolic who's with Levy GL2, which is the short root GL2. So the short simple root of G2 sits inside this GL2, and the long simple root of G2 sits inside the unipotent radical N. And so N mod Z here is essentially the symmetric cube representation of GL2. On F4, this is the parabolic, the C3 parabolic. So the Levy is a GSB6. On E8, this is the parabolic whose Levy is a GE7-3, and N mod Z in this case is the 56-dimensional sort of defining representation of E7. So before I go on to the next slide, I called the Levy here is called H because in all of these cases, you can just look by inspection if you want. In all of the cases, H here has a structure of its symmetric space is a Hermitian tube domain. So the H here is for Hermitian, and that'll be important later or soon. Okay. So this is the Heisenberg parabolic, and the Fourier expansion of the modular forms on the exceptional groups is along this parabola. Okay. So suppose you've got a modular form F of some even weight L on your group G. The even isn't very important, but just for a certain technicality, I'm going to keep it even for this talk. Now, what you can do is you could take this one-dimensional unipone group Z, that's the center of the Heisenberg parabolic, the unipone radical of the Heisenberg parabolic, and take the constant term of F along Z. And then once you do that, n mod Z is abelian, and so you could Fourier expand F sub Z, this constant term, along n mod Z. And the sort of robust Fourier expansion that's similar to the Siegel modular case is an explicit description of the Fourier expansion of this constant term F sub Z. Okay, so two pieces of notation, just so I could sort of state the theorem precisely. So first, denote by n, I need to denote by n this identification between W and n mod Z. So W is just a name for the abelianization, if you want, of n, and W has on it an H invariant symplectic form, and so that's this thing here. Okay. So suppose L at least one is fixed. So that's going to be the weight of the modular form. And take some omega in the rational vector space associated and the rational points of this vector space W. And assume that omega satisfies a certain positive semi-definiteness condition. Then there are explicit functions, script W sub omega. So these are sort of what's called generalized Whittaker functions, completely explicit. So they're in fact defined in terms of K-Bessel functions. From this Levy subgroup H to the dual of V that have the following property. So if you have a modular form F of weight L for G, then there are Fourier coefficients, so complex numbers AF of omega, so that this is what the Fourier expansion looks like. So you take this constant term F along Z, and then you plug in this unipone element, n of x, in n mod Z, and you plug in an element H in the Levy subgroup of the Heisenberg parabolic. And what you get is first sort of a constant term of F along the whole unipodon, which I'm going to say something about on the next slide. And then a sum of terms of the following form. So e to the 2 pi I omega, the symplectic form, the symplectic pairing of omega with x. So that's just a way of sort of parameterizing the characters on this unipone group N, the unitary characters. And then once you do that, what's left is this sort of completely explicit function, W sub omega applied to H. Okay, and so let me just go back to the Fourier expansion of, here we go, the Fourier expansion of Siegel modular form. So it's supposed to be completely analogous with this Fourier expansion. So in this case, these explicit functions of W sub omega are exactly the analogs of these exponential functions, e to the minus 2 pi trace 2y. This is the Fourier expansion, complete Fourier expansion of this constant term f sub z, without saying what the constant term of f along n is, but one could say what that is. So the constant term of f along the unipone group n is a sum of 3 terms in general. So first, I need to, this is valued in, I'm taking everything valued in this VL dual. So to fix a basis, a particular sort of rational weight basis for this 2L plus 1 dimensional representation, going from VL to V naught to V minus L. And then there are 3 terms in this, 3 potentially non-zero terms in this constant term. So you've got multiplying VL, a holomorphic modular form of weight L on the Levy. So remember that I mentioned that both Levy subgroup H in all of the cases, it has its symmetric space is a Hermitian tube domain. So it makes sense to talk about sort of holomorphic modular forms on H. And so you've got one of those of the same weight L. You've got its complex conjugate multiplying this V minus L. And in the middle here, you've got a ratio of zeta factors, zeta of L plus 1 over zeta of L, times some complex number, beta of F. So a few things to mention sort of right off the bat. So the first thing is that it'll be important later that I've normalized. So one could just absorb this ratio of zeta factors into the beta, but it turns out that it's good not to do that. So to define beta as the thing multiplying this. So one surprising corollary, so that was maybe a lot of notation. So just one quick takeaway at this point, at least a surprising corollary of the explicit nature of this theorem is the following thing. So if you take integer L at least one and a modular form F of weight L for one of these groups, then you can say the following thing. So if the function F is bounded as a function on G of the Adels, then it's necessarily cuspidal, and so in particular is rapidly decreasing. So bounded plus satisfying this differential equation implies that it's rapidly decreasing. An analogous thing is true for Siegel modular forms, but I don't know how general to expect such a result. It comes from sort of the proof at least is sort of very explicit in terms of what this Fourier expansion looks like. Okay. So because one has this Fourier expansion, you can make the following definition. You can say the Fourier coefficients of your modular form F are these numbers AF omega, beta F, and the Fourier coefficients of the holomorphic modular form Vf. So you take your function F and take the constant term V of F along Z and look at the Fourier expansion, and there's these complex numbers that appear in the Fourier expansion. So these AF of omegas here, and in the constant term, you have this beta of F and the Fourier coefficients of this holomorphic modular form phi sub F, which makes sense because phi sub F is a holomorphic modular form, so it does have Fourier coefficients. So those are the Fourier coefficients of F. And so now you could say, suppose you've got some ring R inside the complex numbers. You say that the modular form F has Fourier coefficients in the ring R if all of these numbers, AF of omega, beta F, and the Fourier coefficients of phi F are in the ring R. So this is maybe one of the key definitions for the talk. So I wanted to make a few sort of warnings and reiterations, I guess. So the first thing is that the definition completely sort of crucially uses the theorem on the Fourier expansion in order to sort of say, in order to make this definition. It's sort of an output of the theorem. And there's no sort of a priori reason to expect any modular form to have Fourier coefficients in a small ring, such as Z or Q bar. So that'll be the second half, or the ending part of my talk. I'll talk about examples for which that's true, but there's no sort of a priori reason to expect that as far as I can tell. And then finally, I just want to mention, so if you're thinking about sort of holomorphic modular forms on GL2, you know that the algebraicity of the Hecke eigenvalues implies the algebraicity of the Fourier coefficient. So, so that's sort of completely false in rank bigger than 1, in particular for these groups. So there's no sort of, again, so there's no sort of reason to expect this definition to be interesting a priori, as far as I can tell. Okay, so in terms of the proof of the theorem, the proof of this Fourier expansion theorem, there's a few, there's basically just one sort of simple idea. So fix some unitary character chi on this unipotent radical end of the Heisenberg parabolic. And what you do is you consider all functions W chi from G of R to this VO dual that satisfy the following properties. So they have a K equivariance property. W chi of GK is K inverse applied to W chi of G for all K in this maximal complex subgroup K and all G and G of R. They have a left invariance, a left equivariance under the unipotent group N. So namely W chi of NG is chi of N, W chi of G for all N and N in this unipotent radical and G of R. And then finally they're annihilated by this differential operator DL. And moreover, a moderate growth. So once you impose all these conditions, you can, it turns out you can just make a complete and explicit analysis of every function that satisfies all of these properties. And what happens is that if chi is a non-trivial character, a non-trivial unitary character, there's a most a one-dimensional space of such functions, and you can just write down what that function is, and that's the W's that appear in the Fourier expansion. So let me mention that a representation, so from the point of view of representation theory, what this analysis does is it implies a sort of a multiplicity one property. So namely, if you have a non-trivial unitary character, and you look at this, one of these representations, pi sub L, so if L is sufficiently large, this is a discrete series representation of your group G. And you can look at the Hom space, that chi, the NR equivariant Hom space from pi L to chi. And then this analysis proves that this Hom space is the most one-dimensional if chi is non-trivial, and it's zero unless chi satisfies this positive semi-definiteness condition. So if chi does not satisfy this positive semi-definiteness condition, then there's no such, this Hom space is zero. Okay, and for generic chi, so for chi in the open orbit of H on N, the multiplicity one result was proved by, was previously proved by Walla. So that's just sort of the proof of this theorem. You just sort of make an explicit analysis of all of these functions, and then you can, it turns out that the answer is very nice, and you can just sort of write it down. So the second, the sort of second half or second part of my talk is about examples of modular forms with Fourier coefficients in small rings. So at first I didn't really know what to expect in terms of whether or not there should be any examples or many examples of modular forms with Fourier coefficients in small rings, but it turns out that there's at least some one could prove some sort of modular forms one can write down explicitly, and also prove that the Fourier coefficients are in Z or Q bar. So this is the sort of a complete list of all of the examples that I know at the moment. So on E8, there are two examples, a so-called minimal and next to minimal modular form. So these are weight 8 and weight 4. So the minimal one is weight 4, and the next to minimal, the so-called next to minimal modular form is weight 8. And one can show that they have, these modular forms have Fourier coefficients in Q. So let me reiterate here. The Q here means that these AF of omegas are in Q. There's a holomorphic, a non-zero holomorphic modular form here for phi F. It has Fourier coefficients in Q, and then the beta of F is in Q. So that's why one uses this ratio of zeta factors in this definition. So the thing multiplying this V naught is a rational multiple of this ratio of zeta factors. Okay. So this result on the minimal and next to minimal modular form uses some Q input from work of Witek and Gordon Savin. And many Fourier coefficients are zero for these examples here. On E6, there's a weight 4 modular form, all of whose Fourier coefficients are integers. And this example illustrates, has a different property. instead of having lots of Fourier coefficients that are 0, it has what's called a distinguished property. So that's a classical term referring to a special property of certain Siegel modular forms. And an analogous thing is true here. So if time permitting, I'll mention what that is. And it's sort of closely connected to arithmetic invariant theory. And the examples from 1 and 2 here are not cusp forms. And these are only sort of 3 examples. So the last sort of result is that on spin 8 and G2, there are non-zero cusp forms of arbitrary large weight, all of whose Fourier coefficients are in the algebraic closure of Q. And so these examples are constructed using a theta correspondence. So the dual pair SP4 and SO44, and the examples on spin 8 and G2 are constructed using the theta correspondence. And so to maybe reiterate, so the theorem says that there are some modular forms and exceptional groups that possess a sort of surprising arithmeticity. Namely, these Fourier coefficients are in Q bar. Okay, so let me start with the proof of this last part, the construction of cusp forms. There's a theta lift, like I mentioned, between SP4 and SO44. And what you can do is you could start with the holomorphic Siegel modular cusp form on SP4 of some weight L, and you can lift it to SO44 and call the lift theta of F. And so by a general result of Rallis, what you get is a cusp form on SO44. Theta of F is a cusp form. Now, so that's just a sort of a general result. But the theorem is that with appropriate Schwarz-Bruhat data for the Weil representation, so remember that the theta lift, you need some data, you need some sort of Schwarz-Bruhat data in the Schrodinger model for the Weil representation in order to define, in order to get sort of a concrete automorphic form. So for appropriate data, this theta of F is a non-zero weight L modular form on SO44. So recall that if you have a group SO4N with n at least 3, so in particular SO44, there's this notion of modular forms. And the weight here, the weight L, is the same weight as the input that you started with, the holomorphic Siegel modular form on SP4. So that's one part of the result. But the more important part, the more interesting part, at least to me, is that you can concretely describe the Fourier coefficients of this lift theta F in terms of the Fourier coefficients of the modular form F. And so in particular, if you start with a Siegel modular form F on SP4, whose Fourier coefficients are algebraic integers. So for example, a level 1 modular form that's a Hecke eigenvector, then its lift theta F, the lift theta F, its Fourier coefficients are non-zero algebraic integers. Okay. So let me just mention sort of briefly that this lift is an analog of, if you will, the Saito-Kurokawa construction. So there's a special, sort of a very special theta lift between SL2 tilde and SO2n. So it's special in the sense that both sides of this, on both sides here, you can talk about holomorphic or anti-holomorphic modular forms. And this sort of special theta lift was studied by Doi Naganuma, Niwa Shintani, Kudla, Oda, and Rallis and Schiffman, sort of for various levels of generality. And in this sort of special theta lift, you can sort of talk about concretely the Fourier expansions of the modular forms on both sides. And so this sort of an analog of that sort of special theta lift. So what is the formula? So it's very simple. So the Fourier coefficients of an element, the Fourier coefficients of theta of F, so theta of F lives on SO44, and so its Fourier coefficients are parameterized by elements of this, the abelianization of the unipole radical, the Heisenberg parabolic on SO44. And so that abelianization looks as follows. So it's a 2-dimensional representation of GL2 and a 4-dimensional representation of SO22, the tensor product there. So a typical element of this space is of the form E tensor VE plus F tensor VF. So E and F make a symplectic basis of this 2-dimensional representation of GL2. And then from such an element, omega, you can write down this sort of matrix of 2x2 matrix of inner products of these orthogonal, of these vectors VE and VF in this, which are in this orthogonal, in this quadratic space V4. So you get this 2x2 symmetric matrix, and the Fourier coefficient formula of the lift is as follows. So the omega Fourier coefficient of theta of F is the S omega Fourier coefficient of F, at least if omega is sort of integral and primitive in a certain sense. And if omega is not primitive, then you just have a slightly more complicated formula. And again, so this formula implies that if the Fourier coefficients of F are in some ring, then some ring R, so for example, Z or Z bar, the algebraic closure, the algebraic integers, then so are the Fourier coefficients of theta of F. So that's the lift to SO44, and a simple corollary of the lift is to produce non-zero cuspidal modular forms of weight L on G2 with Fourier coefficients in Q bar. So, and you have to put in a restriction here that L is at least 16 and even for things to converge. And so this corollary produces cusp forms of arbitrarily large weight on G2 with Fourier coefficients in Q bar. So the proof of the corollary is very simple. You embed G2 into SO44, and you take one of these theta lifts, theta of F on SO44, and you just pull it back to G2. And what happens is, so it's very easy to check that this pullback, capital F, it's still a weight L modular form in the sense that I'm talking about. It's annihilated by the special differential operator on G2, and it's still cuspidal. So you get a cuspidal modular form of weight L. And then the crucial bit is that when you do this pullback from SO44 to G2, the Fourier coefficients of the pullback on G2 can be easily described in terms of the Fourier coefficients of the theta of F on SO44. So namely, they're just finite sums of Fourier coefficients of theta of F. And the fact that they're finite sums is, it sort of crucially uses this positive semi-definiteness condition for the non-vanishing of the Fourier coefficients of modular forms. So it's very special to these modular forms and not something that you could, that you would expect for sort of general automorphic forms. And let me mention that, so this idea to construct automorphic forms, cusp forms in G2 by pulling back from an orthogonal group goes back to Rawless and Schiffman, and also work with Lee and Schweimer. So they constructed cohomological cusp forms on G2 by theta lifting from SL2 tilde to SO34 and then pulling back to G2. And so what one gets when one does that is sort of are different cusp forms on G2. Okay. So I only have 5 minutes left. So let me just, instead of trying to, rush through as many slides as I can get through here, let me just say a few other things. So there's this, a modular form, a weight 8 modular form on E84, which is called the next to minimal modular form. And this is another modular form that I can prove has rational Fourier coefficients. And so I wanted to mention that, so I'm working here on quaternionic E8, so the form of E8 with row rank 4, and on split E8, there's an analogous automorphic function which has been studied before. So this analogous sort of next to minimal automorphic function on split E8, it's spherical at every place, at every finite place it's spherical, and also at the Archimedean place. And it's been studied recently by Green, Miller, and Van Hove, and that paper has an important appendix by Chibatara and Trapa, and so they sort of studied some of the vanishing properties of the Fourier coefficients on split E8, and also recently Gravich, Gustafson, Kleinschmidt, Persson, and Sahi have been looking at some of the among other things, some factorizability properties of the Fourier coefficients of this next to minimal automorphic function on split E8. So on quaternionic E8, there's this analogous automorphic form, and it's defined in terms of some special value of some Eisenstein theories outside the range of absolute convergence. And using results of Gordon-Savin on some spherical constituents of degenerate principal series being small, using this as a key input, one can prove that this next to minimal modular form has many Fourier coefficients which are 0. And then to prove that it has a rational Fourier expansion, you use this result of Savin to give that lots of the Fourier coefficients are 0, and then you use sort of explicit computation to check that the other Fourier coefficients are rational. And so the key part of the proof of this rationality result, this explicit computation giving the rationality of these Fourier coefficients, is an explicit computation of a certain Archimedean-Jacquet integral on some orthogonal groups of signature, in this case SO311. So you do some explicit computation of an Archimedean-Jacquet integral on SO311, and that's basically enough to get the rationality of the Fourier coefficients. Of the Fourier coefficients of this next minimal modular form. So that's about all I have time for. So I'll just skip to the last slide and say thank you for your attention.
Well, thank you very much. Are there any questions?
Maybe
So I have a question, sorry.
Amos, please.
Yes. Hi, Aaron. Very nice talk.
Oh, hi.
Yes. So I didn't understand. Were you looking at all quaternionic discrete series or just small ones somehow?
So not just the small ones. But also not all of them. So what I'm looking at is all of the quaternionic discrete series for which the K-type, the minimal K-type, is relatively simple.
I understand.
Which the minimal K-type is just one of these,
Yes.
only sees the representation theory of SU2 and doesn't see the representation theory of this, it doesn't, just sort of this L here acts through the trivial representation. So that's the restriction.
But what does this mean in terms of the nilpotent orbit for classical groups? Do you know what is the associated variety?
It doesn't impose any restriction on the orbits. It's a large family of these discrete series. But maybe to answer your question.
The annihilator is large. I mean, so you wrote down some differential operator that was in the annihilator of the module. And probably,
the orbit, the associated orbit, that puts some restriction on it. I just was wondering if you knew what it was.
Right. So yeah. So certainly the orbits are restricted by virtue of being quaternionic discrete series, but just not by having this K type is what I was trying to say. So in terms of the key fact, or a useful fact, is that these quaternionic discrete series, they embed into degenerate principal series for the Heisenberg parabolic. And so
the ones that you were looking at have that property.
And so, sorry, say again?
The ones that you are looking at are embedding inside the Heisenberg degenerate parabolic Eisenstein series?
Yeah, so all do. And so these embed into degenerate degenerate principal series with just a character on the Heisenberg parabolic, and then all quaternionic discrete series, they embed into sort of a degenerate principal series with just a finite dimensional representation.
Okay, so then the orbit cannot be bigger than the Richardson orbit of the Heisenberg. Okay, so that's not so large, but all right. So
exactly.
Then, okay, so now I understand. Now, do you have, so you wrote down some Fourier expansion on Z by restricting to the center of the Heisenberg. Can you write down the full automorphic? Did you write down all Fourier coefficients? I mean, did you write down enough to reconstruct?
Thank you for asking. No, I forgot to mention that. So the answer to your question is no, but so this is the only Fourier expansion that I write down. For me, this is plenty. So there's the following fact for these particular groups, for this list of groups. Oops, I have a touch screen, and so I just touched the screen and I did something I didn't want to. For this list of groups on this slide, so all the ones that I consider in this talk, the following fact is true. If you have an automorphic function, any automorphic function f on one of these groups, and you take the constant term along z, and you get 0. If that happens, then the original function you started with was 0.
Yes.
So for me, for my purposes, this Fourier expansion contains quote unquote all the information of the automorphic forms for these groups. In that sense.
The statement that you made is sort of a statement over the complex numbers, and you're finding interesting algebraic numbers. So the question is, are all Fourier coefficients algebraic? That would lead to some identity. I don't know if, so maybe you can make some statement along that line. There are other Fourier coefficients, not just expansion.
Right, yeah. So
perhaps they're all algebraic, and that would be an interesting statement.
Right, so so one can try to sort of Fourier expand along Z and maybe do some Fourier Jacobi expansion, or one can try other parabolics because these quaternionic representations embed into degenerate principal series for P. For the Heisenberg parabolic, I've only tried to do this Fourier expansion, but I know you and Dimitri and Kleinschmidt and Gustafsson and Daniel Pearson have, of course, considered all these sort of various different types of Fourier coefficients, for example, for the next minimal representation.
Okay, that's all. Thank you.
Excuse me? Excuse me?
I can't see who's talking.
Can you please comment on arithmetic properties of Fourier coefficient besides being belonging to this or other field? Because the Fourier coefficient of Hecke eigenform, they have something to do with counting algebra number theoretic problem. Is that right?
I'm not sure I understood what the question was, but so maybe it's probably to sort of partially comment on what you said. If you knew if you had some automorphic function, if you had an automorphic function which had q-bar valued Fourier coefficients, and it was a Hecke eigenform, then I believe you would deduce that the Hecke eigenvalues are algebraic. I mean, I haven't proved that, but that seems very highly plausible to me. But the only remark I was making before was that the converse is sort of very far from true. Above, as soon as you're above rank 1. But I don't think that was, I'm not sure if that was really answering your question.
Well, I might ask it later. Okay, thank you very much.
Okay, thank you.
Perhaps the factorization could help to relate to what Nadia was saying, if you can factorize.
Maybe I have a question. You just a word you mentioned. You said it is related to arithmetic invariant theory for E6 something. Yeah, 4.
Yeah.
So can you talk a little bit more about that? What is meant by this statement?
Yeah. So there's this result here that I didn't have time to mention. But the Fourier coefficients are parameterized by elements of this rational vector space W. So on E6, this W is essentially it's essentially a 20-dimensional exterior cube representation of GU33. But anyway, it has a rational structure, and the orbits of the levy and so the levy acts on this space parameterizing the Fourier coefficients. And over the complex numbers, there's one open orbit, but there are infinitely many rational orbits. And so to me, the term arithmetic invariant theory means understanding sort of the difference between the rational and the complex orbits. So there's one complex orbit, but there's infinitely many rational orbits. And so what happens is this modular form on E6 that one can construct, it has the property that for one of those rational orbits, there's non-zero Fourier coefficients, but for all the other rational orbits, the Fourier coefficients are 0. So it sees sort of the arithmetic of those of the orbits on this this particular sort of pre-homogeneous vector space W. And the proof also sort of involves, the proof of that, of course, involves some quote-unquote arithmetic invariant theory, because one is getting a result about some rational orbits being distinguished among other orbits, among all the orbits.
Yeah. Thank you.
Yeah, thank you.
Can I ask a question too? Hello? Can I ask a question? So some of your results, you have, like, for example, the one that's now showing and a few others, you said there is a modular form of set and weight and such and such. To what extent there is some characterization? I mean, is this unique or is this because of the construction? I mean, this might be a very naive question. I just wanted to learn if there is some kind of characterization results.
So the ideal result for me would be something like you're saying, a characterization. So saying these are, every modular form of weight L has, or there's a basis of modular forms of weight L for which all the Fourier coefficients are in Q bar. I don't know if that's true. It's something that's sort of the most optimistic thing one could guess. So that would be one form of a characterization. But I don't have any sort of results that strong. So at the moment, when I say that there is a modular form with non-zero modular form with some Q bar value Fourier coefficients, for example, that's just the best I can do is sort of to construct it concretely in one way or another and prove that it has those properties. So, so for example, all in this theorem where I say that there are these modular forms with these four equations, these are all sort of concretely constructed in one way or the other. So on E8, they're concretely, these particular automorphic functions are concretely constructed as regular values of Eisenstein series. On spin 8, the modular form is constructed via theta lifts. On G2, there are pullbacks of theta lifts from spin 8. And on E6, basically what you do is you take one of these things on E8, the weight 4 modular form on E8, and you pull it back to E6. So in all of these cases, there's sort of completely explicitly constructed from Eisenstein series or theta functions and pullbacks.
So I have some other things to say, but perhaps we can chat separately, Aaron. So
Okay.
sort of suggestions and so on.
That sounds good.